In this Organic Chemistry 1 lecture, we will examine the relative strengths of acid using a Pka table that contains a spectrum of very strong to very weak acids. The Pka scale is a logarithmic scale in which 1 Pka unit corresponds to an order of magnitude difference. In this table, we will see acids that are completely ionized in water and thus have small negative Pka values. We will also see the progression of acids to very weak ones that have large positive Pka values. In our interpretation of this data, we will understand what structural features are present in the functional groups that differentiate a strong acid from a weak one. Factors to be considered will be resonance, induction, hybridization, and electronegativity, to name a few. One common feature of exceptionally strong acids is that their conjugate bases can stabilize the incipient formal negative charge by some phenomenon such as resonance or electronegativity. As we investigate weaker acids, we will see that very subtle differences in structural features are responsible for increases or decreases in relative acidity. The big picture, however, is what will ultimately stabilize the conjugate base. As we observe, the stronger the acid, the weaker the conjugate base, and vice versa. So a weak acid has a very reactive conjugate base, meaning that the base is unable to support the negative charge on it. We will then apply this understanding when choosing an appropriate base to deprotonate an acidic functional group to achieve equilibrium towards the products. Our key concepts and lecture learning outcomes. Upon completion of this lecture, you should be able to locate different functional groups on the Pka table and find their associated Pka values, rationalize using electronegativity, hybridization, resonance, or induction why a functional group is strongly or weakly acidic, classify different functional groups within a molecule and assign their Pka values, compare two Pka values to determine which functional group is more acidic, analyze an acid-base reaction, and utilize Pka values of the acids to determine which side the equilibrium lies on. Recall some common acids used in organic chemistry and recall some common bases in organic chemistry. So basically, we're going to learn how to interpret the Pka table of acids, and then we're going to understand the differences in those functional group acidity, and we're then going to learn what are some common acids and bases we use to carry out reactions. So let's go ahead and start by examining a Pka table. So the relative strengths of acids and their conjugate bases. So this table is fairly lengthy. In the first column here, we have acids from very strong acids to hexafluoroantimonic acid, down to very weak acids such as ethane. In column 2 is the approximate Pka. So for the strongest acid listed, it has a negative Pka number, so negative 12. If we scroll down, the weakest acid at the other end of the spectrum has a positive value at 50. So we're dealing on a scale of about negative 10 to 50. The last column is the conjugate base. So essentially we can see for this acid we're removing an acidic proton. This acid is neutral, so the conjugate base bears a formal negative charge after deprotonation. And so as the inverse relationship, the strongest acid forms the weakest base. So as we go down this column here, you can see that some of these bear negative formal charges, some of those are neutral. So that means the starting acid has a positive formal charge, and when it loses a proton, it ends up neutral. So as we scroll down, we're increasing in base strength. So this anion here is the strongest base there is. So the weakest acid has the strongest conjugate base. Since there are so many functional groups on this column, I've drawn this line here in red between the positive pKa values and the negative pKa values. And so what we will do is examine the acids above the line in a separate slide and those below the line in a separate slide, pointing out different functional groups present in each sort of category and what factors affect their acidity. So the strong acids, everything above the line, you can see that the pKa values all have negative signs in front of them. So that indicates that they're very strong acids. So let's understand sort of the difference between an organic acid and an inorganic acid. So when I say an inorganic acid, I'm typically referring to acids such as HF, HCl, HBr, HI. So the hydrohalic acids, other acids as we see on the table, nitric acid, HNO3, H2SO4, sulfuric acids. So hydrohalic acids. So we have nitric acid, we have sulfuric acid. So these are common inorganic acids that we see on the table. So what I'll do is I'll explain these first, and then we'll get to these organic acids that we see here sort of in the middle of the table. So looking at these acids, the hydrohalic acids, nitric and sulfuric acids, we can explain why they're such strong acids based on things that we know about electronegativity and resonance stabilization. So if I draw a line sort of separating these acids, and I'll just draw a general reaction for the hydrohalic acids. So HX, where X is the halogen. If we react that with water, and as we saw, water is a leveling solvent. So what that means, here's your acid, here's your base. So the halogens all have 3 lone pairs, 1 bond. The water is acting as a base to abstract the hydrogen. We're then cleaving this bond, and the electrons in that bond go on the halogen. So what we end up with is the conjugate acid of water called hydronium ion. Now this is bearing a formal positive charge, plus we have the conjugate base of the starting acid, and this is halide ion. So hydronium ion. And then this is your conjugate base. So we can understand why these hydrohalic acids are so acidic is that this bond that we are starting with, this HX bond, the halogen has 3 lone pairs, so it's very electron rich to begin with. We know from electronegativity, they have high electronegativity values, so we can say this is delta minus, and then the proton is delta plus. So the bond is really ionized so that the electrons here are almost residing on the halogen to begin with. So this acid gives up that proton very easily. It donates it. So if we think of it in terms of the Lewis definition, the base is donating this electron pair to that proton. The proton's accepting that lone pair. The X ends up as the Lewis, as the conjugate base, because then it's accepting this lone pair of electrons that's in the bond. So we have our acid, our conjugate base, our conjugate acid. So the conjugate base, this halide ion with the formal negative charge, halogens like having a negative charge, so that's now they're in their Nobel configuration. So it's able to stabilize that negative charge. So we can rationalize their acidity based on electronegativity. So another thing I want to point out is the direction of this arrow, why it's pointing this one way, meaning that the equilibrium is fully shifted towards the products. The way we can rationalize that is through using the Pka values. So let's go ahead and we're going to say X is HI. So we're hydroiodic acid where X is I. We find HI. It has a Pka of -10. So we're going to write that number here. So now let's find the conjugate acid. On the product side, that's hydronium ion, H3O+. We go on the table, we see H3O+ here. That has a value of -1.74. So let's write that down. So we are able to determine the location of the equilibrium, either reactants or products, based on these pKa numbers of the acids. This is strong, this is weaker relative to that. So when we're dealing with acidity, we're always dealing with relative to something else. So we know that the more negative the pKa, the stronger the acid. So the equilibrium always lies to the weaker acid-base pair. So that's why we draw the arrow completely this way towards the products. This also brings up another important concept in that water is what is called a leveling solvent. Meaning that for very strong acids, when dissolved in water, you will always form this common conjugate acid hydronium ion, because the acids are always giving up a proton. So water is a leveling solvent. It acts as a base to abstract that, and you're always going to get this. And we will see that when we look at nitric and sulfuric acid. So let's go ahead and look at those. And we can invoke resonance for why they are acidic as well. So let's draw out nitric acid. So nitric acid has the following Lewis structure. So notice that the nitrogen is plus, the oxygen is minus, but overall the molecule is neutral. The plus balances the minus. Again, we're reacting this with water as our base. So we're abstracting this hydrogen. We are then cleaving this bond. The electrons go on the oxygen, and we see. So let's draw out the conjugate acid again, and that's hydronium. So hydronium ion. Now the conjugate base. So notice we've generated a formal positive charge, a formal negative charge, but they balance out. They equal 0. These still equal 0, so overall we're neutral. We see the pKa of nitric acid is negative 1.4. Let's write that down. Again, we saw the pKa of hydronium, negative 1.74. Now the difference between those two values isn't huge, so we do set up a back and forth equilibrium. So we can draw a reverse arrow, and so it's important to understand what this arrow means. So it does not mean the species present on the reactant side are equal in concentration to the species present on the product side. So we're setting up an equilibrium that is once it goes forward, it can go backwards. But it's not like these are going forward and backwards at the same rate in 50%, where these concentrations equal these concentrations. That's not what these arrows mean. Just understand that it can go backwards. So let's understand about now the phenomenon of this species here, this conjugate base. So oxygen's able to stabilize the negative charge, but also now there's another reason why this species is stable, and that is resonance. So what that means, resonance is always the movement of electrons, not atoms. So this negative charge can move to form a pi bond, and then we break this pi bond here. So the resonance hybrid for that is the following. So you can see that even though the connectivity is all the same, we've moved these electrons. So really what these hybrids are telling you is that each oxygen-nitrogen bond lies somewhere between a bond order of 1 and 2, because this looks like a sigma bond, but you could actually show resonance between here, and then you break that bond. So it's between a single and a double bond for all of them. So it's really, they're not individual things, they're all one structure in which the nitrogen has a positive charge, and the oxygen is bearing partial negative charges. So that's spread around all the oxygens. So why don't you repeat that same exercise with sulfuric acid to show all the possible resonance structures. To practice that with the arrow pushing and to understand why sulfuric acid is a strong acid as well. So now I want to compare sulfuric acid with this entry here, which is called Paratoluene sulfonic acid, and structurally what are the similarities and differences of those, and why this species is similar to that and what it's used for. So let's go ahead and we'll draw out sulfuric acid. So we can see we have H2SO4, so it actually has two acidic protons. They occur at different pKa, so the first pKa is -9 as listed in the table. And let's compare that to the following molecule that's listed, which is called a sulfonic acid. And it's essentially a carbon-based derivative of sulfuric acid that makes it soluble in organic solvents. So there's the benzene ring. It's attached to the sulfur, and then we have the acidic hydrogen there. So again, the first pKa we see here is -9 for sulfuric acid, and the pKa for paratoluene sulfonic acid is -6.5. And so the presence of this benzene ring is essentially there to help solubilize the acid component when you're running a reaction. So sulfuric acid is obviously soluble in water, but not terribly soluble in organic solvents, which we need to run reactions. So this portion has been substituted with this ring, which makes it soluble. So what I would like to do next is then discuss these species here, and let's draw out those Lewis structures essentially of what they are, and why they're such strong acids. So we have the following species. So it's always helpful when you have these like condensed formulas to draw out what the structures actually look like more in the common Lewis form, so you can tell what functional group they're derived from. So notice they're all bearing this positive charge on oxygen. So they're coming from a parent functional group, which you can see in the conjugate base. So this is an ether, this is a ketone, and then this is an alcohol. So these acids are resulting from when these things get protonated. So let's go ahead and draw out the Lewis structures. So here's the ether, CH3O. So this resembles sort of a hydronium ion, where you've substituted the two H's of the hydronium for methyl groups. So again, this results when you protonate an ether. So our second species is a protonated ketone. So again, the oxygen is positively charged. So ketones can act as bases to be protonated by very strong acids, and so we will see that throughout our studies of organic chemistry. And then the last species here is a protonated alcohol, and so again that in a sense resembles the hydronium ion. So we can protonate the oxygen of an alcohol to end up with this species. And so we will gradually learn the reactions that these are used in subsequent transformations that can take place with them. So essentially, to get these oxygens protonated, we really have to use acids that are much stronger. So again, since equilibrium lies to the weaker acid-base pair, we would have to use something like Paratoluene sulfonic acid to protonate the neutral functional group and end up with these. So why don't we draw that out so you can see how such a reaction would actually take place. So if we're starting with dimethyl ether, and we're treating that with the paratoluene sulfonic acid, so here's our acidic proton. That's at a pKa, again, of -6.5. So what's going to happen This species is acting as the acid. This species is acting as the base. The base is supplying the electrons to abstract the proton. We're then breaking this bond so that the electrons in that bond go onto the oxygen. So we form the protonated ether, and then we're generating also the conjugate base of the Paratoluene sulfonic acid. So we saw this pKa was at negative 3.8. So we would presume that this reaction occurs in the forward direction to favor the products because this is a weaker acid-base pair here. So here's your conjugate acid, here's your conjugate base. Notice the plus is balanced out by the minus. So why don't you, as practice, show how these species here, in individual cases, are protonated by the Paratoluene sulfonic acid. So show the neutral functional group getting protonated by Paratoluene sulfonic acid to form these. So run the similar reaction as we've done here, where you actually form those acids. So moving on to the weaker side of this line, so all these now are positive pKa's. Let's go ahead and examine the functional groups that we see and some of the trends responsible. So the first trend, let's talk about the periodic trend. So let's look at the following acids. So methane, ammonia, water, and HF. So we're going across the periodic table, looking at those specific acids. Let's locate their pKa values on the table and then discuss the trend of acidity and why we observe that, and then we'll also look at their conjugate bases and discuss that trend as well. So we're looking for methane. We don't see methane specifically listed here, so really we're looking for a surrogate, and that would be ethane. So an sp3 hybridized carbon, CH bond. So we see that here in ethane, so that's 50. Let's go ahead and write that number down. So we'll say here pKa, this is 50. Let's go ahead and find now ammonia. So as we're scanning, we see right there, ammonia is listed exactly, so 38. So let's go ahead and find water. We can actually scan up and we actually see water, that's 15.7. Next, we're looking for hydrofluoric acid. We're scanning up. We do see that exactly, so that's 3.2. So again, we just make a simple note here. So the smaller the pKa number, the stronger the acid. So we can say stronger and then weaker. So let's just use terms like this because we're comparing them relative to one another. So the acidity trend is increasing this way. So let's demonstrate that with an arrow. So increasing acidity. And so we can rationalize that based on the periodic trend of electronegativity. So we know that as we move across that row, the electronegativity increases towards the fluorine. So what that means is that the conjugate base is better able to stabilize the negative charge that's put on the heteroatom, or carbon in that case, of the resulting conjugate base. So let's draw out those conjugate bases so we can understand the inverse relationship between acidity and basicity. So even though I won't push the arrows of showing a base abstracting the acidic proton, that's an exercise you should do to prove to yourself what's happening using the arrow pushing formalism. So notice that in each case, there's only one type of hydrogen. So essentially, we are removing a single hydrogen to form the conjugate base. So in this case, we have CH3, and then carbon is bearing a formal negative charge. So now if we remove one from ammonia, we have NH2. Ammonia starts with a lone pair, and it's getting a lone pair, so it's negative. We're removing a hydrogen from water, so we're forming hydroxide. So it starts with two lone pairs. It gets a third, so it has a negative charge. Then finally, we're forming the fluoride anion. That's starting with three lone pair. It gets a fourth, so negative charge. So notice the conjugate bases across this trend all bear a formal negative charge. Now the relationship between these acids and the conjugate base, the stronger the acid, the weaker the conjugate base. So a way to understand that is this atom is able to stabilize this negative charge very well. Because that is stabilized, this species does not want to use a pair of electrons to be protonated by an acid. So conversely, on the other end of this spectrum, this very weak acid methane, its conjugate base, this carbon anion called a carbanion, is a very strong conjugate base. Carbon does not have a high electronegativity value, so it is not happy bearing that negative charge. It wants to use this lone pair to abstract a hydrogen and become neutral again. So let's demonstrate the increasing basicity with an arrow. So that's going this way. So again, this is increasing basicity. So that's an important trend that you want to understand when you're comparing a series or multiple functional groups within a single molecule that have different types of acidic hydrogens. You rank them from weak to strong, and then understand that the stronger acid always is deprotonated first to form a stable conjugate base. And if you have a very weak acid, it forms a very strong conjugate base. So we can rationalize this primarily on electronegativity. So the next trend that we want to examine is based on resonance stabilization. And so we're going to look specifically at an alcohol, so ethanol with a pK of 16, and then another two carbon species, ethanoic acid, with a pK of 4.75. So both of these species have OH, as you can see, and then the OH of the acidic carboxyl group. But we want to understand what structural features make this approximately, so 16, 5, it's 10 to the 11th times more acidic due to the log nature of that scale. Why is the acid so much more acidic than the alcohol? So let's draw those structures out and look at their structural features. So we're having the ethanoic acid, and ethanol. We said that this hydrogen has a pKa of 4.75. This hydrogen has a pKa of 16. So now if you look, you have OH, OH. But why are these numbers so different? And so let me explain again the log nature. So if we assume that it's the pK of 5 and pK of 16, so 16 minus 5 is 11. So what does this really mean? This is 10 to the 11th times more acidic due to the log scale. So again, each single pKa unit is an order of magnitude. So it's important to remember that. So the 16 and 5 difference is 10 to the 11th in terms of the magnitude difference of acidity. So let's point out some of the structural features in the other part of the molecule that makes these two OH acidities so much different. So again, this is just simple observation. This is an sp2 hybridized carbon. This is sp3. So why does that matter? So let's look at the reactions of these with a base. So say we're going to treat each of those with sodium hydroxide. That's our base. This is called a carboxylic acid. So we know that that's the acid component. So I'm not going to put the reaction arrow in yet. I'll show you how the proton is transferred. The base is abstracting that proton. We're then breaking this bond and the electrons are going onto that oxygen. So how do we know it happens that way? So we know oxygen's electronegative. So that means the hydrogen has to be delta positive. So the negative charge of the base is attracted to this partial positive charge. What these things mean is that it's a polar covalent bond, partially favoring more electron density towards the oxygen. So the base abstracts the hydrogen. We know that the arrow flows this way because it's pointing to that negative charge, which we determined from electronegativity. So that's how the proton is transferred. Let's draw the conjugate base. Plus the conjugate acid. So sodium is the counter ion of that conjugate base. Now we're forming the conjugate acid, which is water. Again, important to note, charge balance, even though these both have charges, they're balanced, so net charge 0. Net charge 0 on this side. So if we look at this species here, we can actually see that we can draw a resonance form. So there's the resonance arrow. We can show their actual resonance by pushing electrons onto the other oxygen. So the fact that that negative charge actually resides on both oxygens helps stabilize the negative charge. So let's go ahead for completion's sake. We know the pKa of this acid we find in the table is 15.7. So in the reaction, we see there's a huge difference, 4.75 versus 15.7. This is much weaker. So we can say that the equilibrium favors the forward direction completely towards the products. So now if we look at this treating ethanol with sodium hydroxide. Again, the same rationale. Sodium hydroxide is the base. The base is abstracting the acidic hydrogen. We're then breaking that OH bond. Again, hydrogen can only have one bond at a time. So if we're forming a bond to it, we have to break an existing bond. We use the same argument of electronegativity. This is delta plus, this is delta minus. Let's draw now the conjugate base in this case. CH3, CH2O negative plus the cation balancing the charge. You're ending up now with the same conjugate acid of water, which we just saw above. That's pK of 15.7. Now, this negative charge only resides on this single oxygen. Remember, this is an sp3 hybridized carbon. The electron pairs cannot be delocalized anywhere else in this molecule. They're stuck on this single oxygen. So in the case above, where we saw the negative charge delocalizing onto the other oxygen, there's two oxygens sharing the negative charge, whereas here there's one. So you can think of it as sort of misery loves company. So this is more stable than this is. So that partially explains why this starting alcohol is less acidic. The other factor we look at now in terms of drawing the reaction arrow is the pKa value. So we have pK of 16 for the ethanol and pK of 17.5. Since that is a negligible difference, we would draw the arrow essentially of going forward and backwards to setting up essentially an equilibrium where neither side is particularly favored over the other. So the forward and the reverse reaction are both occurring at similar rates, so that you have essentially 1, 2, 3, 4 species all in the reaction flask as the reaction is occurring. So again, in the top case, if you take ethanoic acid with sodium hydroxide and the reaction goes, you're only having 2 species in the flask as the reaction proceeds, because it's favoring the products. In this bottom equilibrium, you have 1, 2, 3, 4, because the difference in pKa is so negligible. So now I want to talk about inductive effects. And so you can think of these as through sigma bond effects. And the case that I want to compare, again, in acid-base chemistry, you're always comparing things. So you're not really dealing with absolutes. You're dealing with comparisons. So the case we want to look at is the acid case, the carboxylic acid. So ethanoic acid, which we just saw, I want to compare that, CH3CO2H at 4.75, with this species here, CF3CO2H at 0.18. So the difference is CH3 versus CF3. Let's go ahead and draw those out and try to rationalize why there's this increase in acidity. So essentially this essentially 10 to the 5th increase in acidity. So if we draw out trifluoroethanoic acid, and I'm going to put in all the lone electron pairs on the fluorine. And right below it, I'm going to put in ethanoic acid. So this is sometimes called acetic acid. So that's the common name. So we'll try to use the IUPAC nomenclature as much as possible throughout the course, so that we're all on the same page in terms of the formality of nomenclature. So again, let's put our pKa values in. .18. This pKa was 4.75. So again, what are we trying to do here? This is OH, this is OH. Why are these numbers so different? This is much less acidic than this number. So then if we look, we have carbonyl, carbonyl, that's the same. So what is different? Now this carbon has 3 fluorines. This carbon has 3 hydrogens. So we can, just through empirical observation in reporting, these fluorines have a significant effect in increasing the acidity of this number. So the number becomes smaller as we increase acidity. So how do we rationalize that? We rationalize it by an inductive effects. And so again, this gets back to electronegativity. So we know that fluorine is very electronegative, so we can say this is delta minus, delta minus, delta minus. We know that there's not a great difference in electronegativity between carbon and hydrogen. So essentially what is happening? The fluorines are acting as electron withdrawing groups. So let me write that down. The fluorine is an electron withdrawing group. So we know already that this is an acidic hydrogen, it's delta plus. The oxygen's delta minus, and we got that from electronegativity arguments. We know from the prior example that when this is deprotonated, the negative charge from cleaving this bond is generated on oxygen, and that can be delocalized onto this oxygen. So what effect do these fluorines have? So the fluorine basically help support that negative charge through the sigma bond network. So that's what induction means. These negative charges are tugging. They're polarizing this bond towards the fluorine, which means they're polarizing this bond towards this carbon. So they're tugging that negative charge all the way through the sigma bond network. So let me sort of highlight what I mean by that. So they're tugging through that sigma bond network. So in green, I'm highlighting how that happens. So you don't have that phenomenon possible because these hydrogens are not terribly different in electronegativity than that carbon. So the more electron withdrawing groups, again, electron withdrawing, that's supported by electronegativity arguments, the more of those you have closer to that carboxylic acid group or acidic functional group, it doesn't matter exactly, the more acidic the hydrogen is and the lower the pKa number. So now the last trend that I want to look at in terms of acidity is the carbon hybridization trend. So specifically we have sp3 hybridized carbon with a pK of 50, sp2 hybridized carbon with a pK of 44, and then sp hybridized carbon with a pK of 25. So let's go ahead and draw out those structures and try to understand why the hybridization matters in CH acidity. So I think in learning organic chemistry, it's important to understand trends. If you can understand trends and explain them, you will have a much easier time with the material than just trying to memorize things. So let's go ahead and draw out those species. So here's our acid. Again, this functional group is the alkyne. Then we have the alkene. And then we have the alkane. Let's just point out some structural features here before we do anything else. So all of these have one unique type of carbon. This is sp hybridized. This is sp2 hybridized. This is sp3 hybridized. And so that's going to be important for us in understanding this trend. Let's go ahead and write the pKa values now. So we said for the alkyne, we're at a pK of 25. The alkene, we're at 44. And the alkane, we're at 50. So we can see that the acidity trend increases towards the sp hybridization. So stronger, weaker. Now let's go ahead and draw the conjugate bases of all of these, and then we'll circle back around and discuss the hybridization, specifically the contribution of the s orbital to the hybrid orbital and why that matters. So if we're removing the acidic hydrogen, the carbon is ending up with a lone pair and a formal negative charge. So in terms of the conjugate base strength, again, it's an inverse relationship. So these are the weaker bases, these are the stronger. So the base trend increases this way. And so if we can rationalize why sp hybridized carbon is a stronger acid based on the following fact that the negative charge is residing on the carbon. And if we look at the contribution of the s orbital, which is closer to the nucleus than the p orbital, in this case you have 1 over 2. So 1 and 1 is 2. So the contribution of the s is 1/2. So 50% of that hybrid orbital is s component. That means the negative charge is closer to the nucleus, which stabilizes it more than this case. So the contribution of s here is 1 over 3, so 33%. Here it's 1 over 4, 1/4. So let's just write those numbers down so we can see that trend. So we'll say percent S character is 50%, 33%, and then 25%. So again, the higher the S character in the hybrid orbital, the greater stabilization of the negative charge of the resulting conjugate base. And that's due to the s orbital being a sphere that's closer to the nucleus. So I want to look now specifically at the deprotonation of ethanol, which we saw in a prior slide. So let's draw out ethanol, CH3, CH2, OH. And if we do our standard exercise that we've done so far in this class, we can see that this molecule has three unique type of hydrogen. So we can identify those. We have a methyl group, a methylene, and an OH. So those are the three types. They occur in a ratio of 3 to 2 to 1. So now if we classify those types, we see that's an alcohol. This is a methylene, which we will say is an alkane functional group. And then this is methyl, which is also alkane. So if we go back to our table and we look up the acidities of those functional groups, we'll find that the alcohol was 16, the alkanes are both 50. So if we treat this with a base, and the base I want to use is sodium hydride, so that's a common base we can use in organic chemistry. So sodium hydride's our base. How do we know which of the three gets deprotonated if we have to make a choice? Well, again, the base is going to abstract the most acidic proton. So let's draw out the products that we would form. So there's our conjugate base plus the sodium counterion. Now our conjugate acid is hydrogen. So I'll leave it to you to practice the arrow pushing and showing how this hydrogen abstracts that hydrogen to form this conjugate acid. So here's your conjugate base. This is the conjugate acid. This conjugate acid has a pKa of 35. And so if we look at the difference, delta pKa, 35 minus 16, that gets us 18. So that is essentially a difference in acidity of 10 to the 18th times less acidic. So again, if we're determining how the equilibrium lies, it's lying completely towards the products. This is 18 times less acidic than that. So we're always favoring the weaker acid-base pair when we draw our arrows. So if we take ethanol, we treat it with sodium hydride, we're forming these two species. And so since we're forming hydrogen gas, this is actually evolved from the reaction mixture and it escapes. So essentially in the flask, you're only forming one thing, just this conjugate base. And so that's why we need to know different bases that we can use in organic chemistry. So some of those bases are the following. So N-butyllithium. So that has this structure, CH3, CH2, CH2, and then a carbanion bearing a negative charge with a lithium counterion. So N-butyllithium, that's a very strong base. Another common base is called sodium amide, and that's the conjugate base of ammonia. So Na plus NH2, that's sodium amide. And as we just saw, sodium hydride, that's the conjugate base of hydrogen gas. So don't forget the negative charges. So these are common bases we can use to carry out deprotonations of weakly acidic functional groups. And again, these are all strong bases. So base strength increases in that trend because if we look at the conjugate acids, and their associated pKa's, we saw that was 50. For ammonia, we saw that was 38. And then for hydrogen, we saw that was 35. So acidity increases through this trend. So again, the relationships are different. Functional group acidity increases, conjugate basicity increases this way. So we use these common bases to favor forward equilibrium in deprotonation events. So one thing, getting back to our main title, OH versus CH acidity, one thing we do not want to do when we're considering a molecule like this is deprotonate the wrong functional group. Again, we're deprotonating based on the pKa value. The lower functional group is always deprotonated first. So as an example of what not to do, again, in our consideration of ethanol above, we already determined the pKa's of those functional groups. If we were asked to determine what the conjugate base was, and somehow we drew the following, we would know that this cannot be correct because we've used this base to deprotonate a functional group that is a weaker acid than the existing stronger acid within this polyfunctional molecule. So this reaction will not occur as written because we've proposed that the less acidic functional group is being deprotonated. And again, we can't do that because we have to follow the order of pKa functional group trends. So in our last topic that we'll talk about in this lecture screencast is the Lewis definition of acidity. So Lewis acids and bases. So let's just consider first the simple reaction of sodium hydroxide reacting with hydrochloric acid and what is happening in this case. We have sodium cation, hydroxide anion, plus balance is minus, they're neutral. So how do we know how the base abstracts the proton in terms of the arrow-pushing formalism? We know from electronegativity and the fact that chlorine has 3 lone pairs, that's delta minus. So therefore, the bond is polarized such that the hydrogen is delta plus, meaning that the chlorine, more of the electron density in this bond is residing closer to the chlorine. So we're guided by matching the polarity of these species. The anion is attracted to this partial plus. So in the Arrhenius in Bronsted definitions, we're talking specifically about hydrogen ion concentration, hydroxide ion concentration, the movement of the proton, but in Lewis acid base, we're focused specifically on the movement of the electrons. The Lewis definition of an acid is an electron pair acceptor. A base is an electron pair donor. So in terms of showing the arrows of how that happens, sodium hydroxide is the base. It is donating this pair of electrons to that hydrogen which is accepting them. Because we can only form one bond to hydrogen, this bond has to break. And the electrons in that bond are going on to the chlorine because we've already said that the chlorine is delta minus, so it is accepting those electrons. And another thing I want to point out is the drawing convention. In a lone pair of electrons, there are two, right? 1, 2, that makes the pair. The arrow starts there, so the start of the arrow, and then it ends at the species that's positive. So we match the polarity. The other thing to notice this is a normal looking arrow. So there's sort of a double-headed, so 1, 2. The fact that you have those indicates that those two electrons are both moving. So do not confuse that when you see it in the homework and in the book with an arrow that looks like that, which is called a fishhook arrow, and that only means one electron is moving. So again, when you're showing the pair moving, it has to look like that. And also notice the flow of these arrows, because we're using two of them. Start, end, start, end. So the flow has to be that way. Start, end, start, end. So it's telling you that the flow is sort of in one direction. What you do not want to do is show arrows that look like this. So do not do arrows that look like that. So the reason that sort of does not make sense is because you're showing electrons going into the same place, and we know that from physics those things will repel one another. So we've matched the polarity. We're showing the base donating a pair of electrons, the acid accepting it. We're forming the conjugate acid, which is in this case water. And now the conjugate base, sodium chloride. So the chlorine has accepted the electrons from that bond. We've balanced out the plus and minus, so we're neutral because we started neutral. So what are some other Lewis acids that we will use in this course that we need to know? So one of them is boron trifluoride. That's BF3. Another one is aluminum trichloride. So these are pretty common ones that we will use. And the unifying feature of both of these is that they are both electron deficient, so they do not have an octet. Both of these atoms, boron and aluminum, are sp2 hybridized. So the reason that's important is because we know from sp2 hybridized atoms there are 3 sp2 orbitals plus 1 empty p orbital. So again, the Lewis acid definition is an electron pair acceptor. The boron and aluminum can accept an electron pair in this empty p orbital. So let's actually look at this in context. If you were taking this ketone and you were treating it with boron trifluoride, we can count 2, 4, 6. So there's 6 electrons. It does not have an octet. It's a neutral species. Notice there's no charge. It's neutral. The empty p orbital still exists. So this is an acid. This is a base. The lone pair on the carbonyl oxygen is going to supply electrons, so it's acting as a base. The BF3 accepts those electrons, and we can draw the following product. We've formed this bond between oxygen and the boron now. So again, as a review of Lewis structures, this is neutral, this is neutral. In the product, this no longer obeys that neutral oxidation state because we have 1, 2, 3 bonds, 1 lone pair. So when we do our formal charge calculation, we find that oxygen is going to be a plus and the boron is now going to be a minus. So notice plus balances the minus. Overall, we're neutral because we started neutral. So again, the Lewis base is supplying the electrons. The Lewis acid is accepting them. We've formed this bond. We've accounted for our formal charges being neutral. So aluminum trichloride acts in a similar fashion to what we just saw. So these are common Lewis acids we will see in organic chemistry. So to summarize in this screencast, we've looked at factors affecting acidity. We've examined the relative strength of acids looking at the Pka table. We've looked at electronegativity and periodic trends. We've looked at resonance and inductive effects. We've looked at hybridization effects. We've talked about ranking functional group acidities when determining what functional group gets deprotonated. And we've also then looked at Lewis acids and bases.